Hello Year 12, welcome to the latest instalment. We've just finished vectors this week and we are now looking at vectors for balancing forces, and we will be moving on to moments in our next video. In this video you are learning how to resolve forces into horizontal and vertical components in order to balance forces. So you've already had lots of practice at resolving forces and vectors horizontally and vertically. We're going to look at two scenarios, those where you analyse them horizontally and vertically, those where you look at them in other directions, but it's all to do with resolving vectors. Okay, so in this video you need to be able to state the link between resultant forces and motion. You may already know this, it should just be a recap from GCSE, but I will go through it. You need to recall how to resolve forces horizontally and vertically, and you need to resolve forces parallel and perpendicular to inclined planes. Link between resultant forces and motion first, however. You may recall from GCSE that the movement or motion of an object is dependent on the resultant force. So just quickly, if the resultant force is 0, can you please tell me what happens to the motion of the force? Okay, so if resultant force is 0, hopefully you remembered that the object's speed will be constant. Now it might be 0 or it might be non-zero, but whatever is happening, it won't be changing. So if it's stationary, it will stay stationary. If it's moving, it will move at a constant speed. Therefore, if the resultant force is not 0, so I have a total resultant force on an object, the object speed will be not constant. It will be accelerating, it will be decelerating, but it won't be travelling at a constant speed. This is Newton's first law, and it's really important because we rely on this for lots of the mechanics problems that we're working with. Later on in the course, we will be looking at motion of an object under non-zero resultant forces. But for most of the vector situations and balancing forces situations you're going to experience, you will have a resultant force that is 0. In other words, you will be analysing statics problems, not dynamics problems. This is important because it makes the calculations much simpler. So for example, here I have a picture which shows a piece of wire attached to an object which has a force acting horizontally and a force acting vertically on it. And the question would tell you the object is not moving, so therefore can you calculate the tension in the string and the angle of the string. Notice that you've been given the magnitude of the weight and the magnitude of this force that is pulling in this direction. Now there are two ways that we can attack this problem. I'm going to start with the simpler one, and that is to calculate the resultant factor for F and W and then balance the forces. So hopefully you will remember from this week's lessons that in order to calculate the resultant vector using scale diagrams or simple trigonometry, I take the vector F, I line it up nicely with the vector W, and then draw a resultant force. Now, because I know that this object is stationary, that means that the overall force in this direction must be 0. So in other words, the tension pulling on the string in this direction must be the same as the resultant force pulling on the string in this direction. So that T is equal to R. Now, if I'd done a scale diagram, I could measure the length of R and measure this angle here, and I would have my answer to what T and R are. However, what the exam board are more likely to be looking for you to do is to do some simple maths. So I know that R is going to be equal to the square root of W squared plus F squared, and since T is equal to R, T will be equal to the square root of W squared plus F squared. That is the magnitude of this vector. To calculate theta, I need to use a basic trigonometry relationship. Theta will be equal to tan to the minus 1 of F divided by W. Now note that this is actually the opposite of many of the calculations you will have done this week. You will have used tan is equal to W over F. Just briefly, I want you to pause and tell me why this time it is the opposite way. Okay, I'm hoping you spotted it, but if you didn't, the answer is because theta in this case is this angle here. In the examples you've come across so far, we had theta being this angle here, but in this case, it's this angle here. So in other words, opposite over adjacent is going to be F divided by W in this case, because the line that is opposite the angle is this one. So theta will be equal to tan to the minus 1 of F divided by W. First method of calculating the tension and the angle, and it's quite a simple one, and you have covered that a lot this week in lessons. However, there is a second method that you could use to calculate the tension of the spring and the angle of the string. And there is a likelihood the exam board might ask you to do this. It involves resolving the tension in the string. So, again, you've had lots of practice at this. I can resolve the tension in the string into a vertical component and a horizontal component. Note that it's cos theta when it's going up to the vertical because t is going through the angle, and it is sine theta when it's coming down to the horizontal because t is having to move away from the angle that I've been given. Remove t because I've now resolved it into its vertical and horizontal components, and I can then balance the forces in both directions. So the object's stationary, therefore I know in the horizontal direction the forces will be balanced. F minus th must be equal to 0. There's no overall resultant force, so F is going to be equal to th. So therefore I know the value of F is 30. 30 is equal to t sine theta. Similarly, in the vertical direction, W minus TV must be equal to 0 because the object isn't moving. So W equals TV. So therefore 50, the value of W equals T cos theta. Now, some of you might be looking at those equations and thinking, well, that's all well and good and I could write those equations, but I don't know what I do next because I don't know T and I don't know theta. Well, here's the good news for those of you doing physics. You are usually told either theta or t, and in the majority of cases, looking at exam questions, you are told theta. So in other words, you can just substitute the value of theta into the equation in order to work out t. There is a slight caveat here, and that's for those of you doing maths and further maths. In maths and further maths, you're more likely to be asked to solve these as simultaneous equations. If you want more information on that, please stop me during our next lesson and I will talk to you about it. However, in physics, we are usually told the value of theta. So for example, if I told you the value of theta was 40 degrees, I know 30 equals t sine 40. So I can rearrange to get t equals 30 divided by sine 40 equals 47 newtons to 2 significant places. Simple. I just wanted to give you a couple more examples because I appreciate that resolving forces can be quite tricky. So here's your first one. This is a helicopter and the downwards force, probably weight, is equal to 2,000 newtons and you need to calculate A. The steps you would follow are as follows. Number 1, resolve A vertically. Number 2, balance the forces vertically. And number 3, rearrange to calculate A. I'm just going to pause the video here and ask you to do that manipulation. Okay, hopefully you managed to get the answer, but just in case, I'm going to step you through it. So resolve A vertically. AV equals A sine 74 because I'm moving away from the angle, sine upwards. Number 2, balance the forces vertically. C has got to be equal to AV because it's not moving upwards. So C equals A sine 74. Number 3, rearrange to calculate A. A equals C divided by sine 74. I know C is 2,000 newtons, so A is 960 newtons to 2 significant places. Okay, another problem for you. Calculate the weight of the block that is suspended from 2 pieces of wire, each with a tension in them of 15 newtons. Steps are going to be very similar. Resolve and balance the forces vertically, and then rearrange to calculate weight. Can you please calculate the weight of the block? Okay, so I need to resolve both of these tensions upwards. So in other words, 15 sine 20, that's number 1, and plus 15 sine 20, that's the second piece of wire, is going to equal the weight. So the weight is going to be equal to 2 lots of 15 sine 20, which is equal to 10 newtons. Hopefully you can see that we are starting to see a pattern in how these type of questions are solved. However, the question is, do we always resolve horizontally and vertically? Take a look at this picture and decide what do you think would be the best way to resolve these forces. The answer is we do not always resolve horizontally and vertically. Obviously, we could take R and we could resolve it into its vertical and horizontal components. And with F, I could resolve it into its horizontal and its vertical components. However, instead of doing this, it's much simpler if I just resolve the weight into components perpendicular and parallel to the surface, because then I only have to resolve one force. So when looking at situations, it's important that you resolve in the direction that is the most meaningful. I'm thinking about something slipping down a plane, probably meaningful to resolve parallel and perpendicular to the plane, but also the one that requires the least number of steps. If I do parallel and perpendicular to the plane, I only have to resolve one force, less steps for me. Please note that typically the question will state the directions that you need to resolve the forces in. So for example, it will say analyse the forces parallel to the slope. Well, in that case, you know you're going to have everything acting parallel and perpendicular to the slope. Most commonly, you will have two types of questions. You will have the ones that we've already analysed, where you do resolve horizontally and vertically, and then you will have inclined planes like this one here, where you will resolve perpendicular and parallel to the slope. Just quickly, if I am resolving W parallel and perpendicular to the slope, these arrows represent the two forces, parallel and perpendicular, and these yellow boxes represent the magnitude of each of those arrows. However, I haven't matched them up. Could you quickly please decide which box goes with which arrow? Okay, hopefully you got the following answers. The angle perpendicular to the slope, the magnitude, of the arrow perpendicular to the slope will be W cos 22, which means the arrow parallel to the slope will be W sine 22. If you did not manage to get these boxes matched up correctly, that's because you're not sure on relationships between angles and angles in different places. This one's quite obvious. You can see that's a small angle. This here is a small angle, but you do need to be incredibly confident with working out the angle in one part if you know the angle in another part. So if you're not confident on that, I suggest you go back to GCSE Maths and you check angles inside shapes. Okay, I would like to leave you with a final question which builds and leads towards our second lesson, for which I have not given you a video. Here I've got a picture of a waiter holding a tray. It's got various forces demonstrated on it, and the question I'm going to leave you with, and I would like you all to vote, is this tray stable? Thank you.